So thank you for making it here early. You're going to get a special treat today because I'm going to introduce to you an amazing new feature for data warehouse query processing in the SQL Server Denali release called Columnstore indexes. I'm going to start out by way of a little story. So Alice is a business analyst, and her job is to write queries and generate reports to help generate insight for her business. And today, her life might look something like this when she's trying to analyze data. So she gets an idea about some analysis she wants to do, some plot she wants to create based on the data that she's got in her database. And so she formulates a query, takes some time, writes a SQL statement, and she waits after she submits the query. She waits a little longer, and a little longer. She keeps waiting, and she gets her answer back. And now, what was that analysis she wanted to do again? Okay, she's kind of lost her place. It takes a while to recollect exactly what it was she wants to do and what analysis she wanted to create. So tomorrow, with SQL Server Denali, it's going to be a little different. She gets an idea for the analysis she wants to do. She formulates her query, runs the query, bam, the answer comes back instantly. And maybe she gets another idea about how to tweak the query. She writes a little bit different SQL. She hasn't lost her train of thought. She runs that. She gets the answer back, creates her graph, and gets some insight into her data. So this new feature in SQL Server Denali is all about enabling insight to data. It's about making the experience of business analysts while they're exploring the data much more interactive. And also for end users that are running reports interactively, it makes their experience a lot better because they can get query results almost instantaneously instead of having to wait 10, 20, 30 seconds, a minute, 2 minutes, 3 minutes to get their results. The new Columnstore index feature that I've told you about this morning comes from a project called Apollo. The internal code name of the project is Apollo for this new Columnstore index feature in Denali. And it's really all about accelerating data warehouse queries. So I've already mentioned the new Columnstore index capability, but there's another equally important part of this, maybe even more important, a new improved method of query execution that goes along with this index to accelerate query processing. And I'll talk about that as part of this discussion. So in addition to making SQL Server more interactive, as I mentioned in the little story that I told, it makes the system a lot easier to use by making the developer's job, the database administrator's job simpler. And I'll tell you about why that is as the talk progresses. And it's also going to reduce total cost of ownership because, for two reasons. It reduces the amount of hardware required to get the same level of performance from query processing, so it can potentially save you money on the equipment that you buy and the floor space and the electricity and everything that you have to provide to provision a server. And in addition, it just reduces labor costs. It makes it easier to get that level of performance. So how many of you do BI or data warehousing? Okay, so you're in the right place. That's good. So again, just to recap the data warehouse scenario that most of you are quite familiar with, it's a read-mostly environment. You load large amounts of data. You typically don't change data once it's arrived. You append new data incrementally. Often you have a daily load cycle. And usually you keep data for some period of time, like 1 to 7 years. And it's typical to have what's known as a sliding window scenario, where maybe you'll load data and then periodically purge old data. And that is often made more easy to do by the use of the partitioning feature in SQL Server. So this is an example of a sliding window scenario, perhaps where you're partitioning by year. And you see as we add new data for 2011, that new partition fills up. Maybe we only really care about keeping around 3 years of data at any one time. So once we've accumulated more than that, we can shift out the oldest partition, switch it out, and then truncate it to recycle the space. So data warehouse schemas vary, but it's quite common to use what's known as a star schema in a data warehouse. And this feature that I'm going to tell you about works particularly well with star schemas. This new index type that I'll describe, the Columnstore index, is for the large tables in your database, the fact tables. Typically, you don't need to use it on dimension tables because they're small enough that you don't have to worry too much about speeding up query processing against the dimensions. And it works particularly well for queries that summarize and aggregate data. If you're pulling back large volumes of data, then the query acceleration is not as significant. So again, this is a diagram of a star schema, and you'd put a column store index on fact sales there, that fact table in the middle of the star schema. This is a typical star join query, a simple one. You see in the from clause, there's 3 tables. There's the fact table, fact reseller sales part, and then 2 dimensions. And so if you look, the where clause joins the dimension tables to the fact table and filters on the dimensions, and then we group and aggregate the data. Very typical type of decision support query. Decision support queries may look more complicated than this, but at their core, their building blocks often look like this. And this is the type of query that this new column store index feature and the new enhanced query execution mode that I'm going to describe in more detail, this is the type of query that is really accelerated by this new feature. So it's not unusual to, we've talked to a number of customers during the development of this feature, and it's not unusual for query processing to take 10 seconds to 3 minutes for typical data warehouse queries, these star join type queries on large data marts and data warehouses on SQL Server today. And so the goal is to speed up these queries. DBAs spend a considerable effort tuning the system to get better performance. And there are a number of different ways that you can tune the system. Many of you, I'm sure, are familiar with all these and have done them in your day-to-day work. But DBAs and developers spend considerable time designing indexes, tuning their queries, maybe rewriting the queries or modifying them to get them to run faster. And especially, they spend time modifying their physical database design by building summary tables or indexed views, also called materialized views. And sometimes people use OLAP cubes purely to get query acceleration because analysis services and other OLAP products have a very sophisticated method of building and maintaining summary aggregates that can accelerate a lot of queries. And that's one of the things that has drawn people to OLAP systems, in addition to the analytical and reporting capabilities that they have. They care about OLAP because just because of query acceleration. So because this new column store index feature and query acceleration method can run queries so much faster, it may make it less necessary to use an OLAP system if you were only using it for query acceleration. So at this point, you may want to see exactly what I'm talking about. I've said several times about how the performance is greatly accelerated through this new Columnstore index feature, but let me show you. Here in the Explorer, I want to focus in on dbo.purchase. I have a database here which has 100 million rows, roughly 100 million rows in the fact table. The fact table is dbo.purchase. Let me refresh this to get a better look at it. So you see dbo.purchase here. These are the columns. Now if I look at the indexes on this table, whoops. You see the indexes folder there. There's CI_date. That's the clustered B-tree index on that fact table, that 101 million row fact table. That's on the date column. That's typically the index that you'd use today on a fact table. You'd want to cluster it by date so that you could get date range elimination when you're querying the data to limit the amount of data that you have to scan. But underneath that, you see that icon that says non-clustered Columnstore index. So the data is stored in a different way that I'll describe in a second, but that's the new index that we've created. It's a secondary index. The clustered index is still a B tree, but we have a new index that contains basically a second copy of the data in a highly compressed form, and that copy of the data is going to be used to do query processing, and most queries will only touch that non-clustered index and will never touch the B tree. So on the left, I have a star join query, and you see right here, there's a hint right there. It says with index equals CI date. So that index hint is going to force the system to use the B tree to solve that query. So it'll be like it is today with SQL Server 2008 R2 or SQL Server 2008. The performance will be similar. On the right, I've got the exact same query, but you see there's no index hint there. So what the query optimizer is going to do when it sees that query on the right, it thinks that the Columnstore index is the most efficient way to solve this query. So it will choose a query plan that scans the Columnstore instead of scanning the B tree. And so I'm going to start running this query on the left. It's going to take a little while to run. Now let me run this query on the right. So you see that it just finished in just a few seconds. The query on the left is going to be running for a while. So let me run it. There's actually several more queries down here, all of which touch that fact table. So it took 24 seconds to run on the left. So let me run all 5 of these now on the right. So it took about 5 seconds to run all 5 of those queries. And if I run this one again, it just took about a second. So in fact, with a completely warm cache, it just takes about a third of a second to run that. This is 101 million rows of data on my laptop, okay? This is a 2-year-old laptop. All right? So it's really stunning. I mean, we're talking, so that particular query had about a 50 times or more speed up on this particular hardware. So this is the biggest advance in query processing for decision support in SQL Server since we bought this software initial snapshot of the code from Sybase in 1989. This is a very, very big deal. So, all right. Now, let's talk a little bit more about how it works. So in a normal B tree or heap structure, data is stored multiple rows per page, and every single column of a row is stored inside that page. Okay? In a column store, we pivot it 90 degrees. We use what's called vertical partitioning and split the data so that each column is stored in a separate group of pages. Right? Now, the benefit of this, hang on. So, how many of you have heard of Power Pivot? Anybody? Okay. So, Power Pivot also uses a column store technology, and it's based on what's called the VertiPack compression algorithm. This implementation in the SQL Server engine actually is based on the same code as Power Pivot and also the same in-memory BI code that's now going to be in the next version of Analysis Services. So we share that technology across all three of those products. We actually took a snapshot of the code that went into Power Pivot about 2.5 years ago when we started building this feature, modified it, and brought it into the SQL engine. So it's built into SQL Server.exe right now. So this extremely powerful analytical query processing capability and compression technology is now shared across all three of those products. So another important thing to mention is that the data in our column store index is heavily compressed. So depending on the data, you'll probably get compression something like anywhere from 4:1 to 15:1 compared to uncompressed heaps or B trees. The nice benefit of that is that a lot more data can fit in main memory. Well, it takes less time to read it from disk in the first place, and a lot more data can fit in main memory at one time. So you can get your entire working set in main memory during normal operation with less hardware or less main memory. So it reduces I/O in a couple ways. One is based on the compression that I described. All right? And the other is due to the fact that you only have to read from disk those columns that you're actually using to process the query. So, for example, that simple query, select region and sum of sales with some conditions, suppose it only touches those two columns. Because of that, we only have to read those two columns from disk. So that reduces the I/O that we have to do. And each of those columns can be very heavily compressed. The index is one part of this, but an equally or perhaps even more important part, again, is a new query execution method. So we have a new query execution method which has an old school name, but it's really very cool underneath the sheets. It's called batch processing. And a batch is a vector-oriented data structure that contains about 1,000 rows of data. Inside of it, each column is represented as a highly optimized vector of values. And that vector processing technology that we use can tremendously speed up query processing by reducing the overhead on a per-row basis for running a query. So we can actually get queries to run with anywhere from 1/10 to 1/100th the number of CPU cycles because this data structure is highly tuned for query execution. You can sort of think of batch processing as like an assembly line, where in the old method of query execution, we process each row one at a time, and that involves interpreting metadata. Like suppose you need to pull the data from a single field out of one row. You have to interpret some metadata to determine where the row is, where that column starts, reach in, copy the bytes out of that column into another location, and then operate on it. Now that takes time. It can take 200 or 300 CPU instructions per row to perform a simple operation on a row, like comparing one column to a constant to do some sort of filter. In batch processing, that overhead is tremendously reduced. It's kind of like going from sort of piecework in a garage where a mechanic is working under the hood of your car to an assembly line where cars are just coming down the assembly line and a worker is just doing the same task again and again, the overhead in the assembly line is much, much lower than it is in sort of one-off type repair jobs. So in addition to this highly efficient style of processing with this new batch mode of execution, we also have better query parallelism. So parallelism in SQL Server is currently based on the exchange operator, and we can scale pretty well up to about 16 cores to evaluate a single query. But beyond about 16 cores, there's diminishing returns. It's hard to get more than about DOP 16 to accelerate a single query. Now, if you have a multi-user workload, you can use all the available resources on a machine that has more than 16 cores. But for a single query, it's pretty hard to scale it beyond 16 on regular SQL Server. That's not the case with our new parallel data warehouse product. Because of its massively parallel architecture, you can scale a lot better. But with regular SQL Server, it caps out at about DOP 16. Now, with the introduction of this new batch processing query execution mode, on regular SQL Server, we can scale to 32 cores and beyond very efficiently. So I've done a test myself where we ran a query in a few seconds against a 2 billion row table on a 32-core machine. And it gave us a 29 times speed up on 32 cores. So it scaled almost linearly up to 32 cores. So query parallelism is improved by this new query execution mode called batch processing that comes with the Columnstore index. Data in the Columnstore index is broken up into what are called segments. So a segment is about 1 million rows of data from the table. And the unit of storage is 1 column's worth of data from one of those 1 million row segments. Right? And instead of storing the data page by page, we store this unit, this column segment, as a unit. Each column segment is stored internally inside SQL Server in a blob or a large object. Right? So when we read the data, the unit of reading it from disk is one of these column segments. And there's a special new kind of object cache in the system that stores those column segments in memory as units instead of storing those 8K byte pages that we store when we read data from a B tree or a heap. Yeah, the question is, on the disk, it's still 8K pages, correct? And the answer is yes. So I can elaborate a little bit on that method of reading. So when we read those blobs from disk, they actually are read in 8K chunks into the buffer pool just using normal reads. But as soon as we get those into memory, we copy that data into a special object that's stored in a new object cache in memory and free those pages immediately so that we don't double buffer. Okay, good question. There are some constraints on using the B-tree index, on using the Columnstore index. So the base table has to be a B-tree or a heap. So I told you about the great compression we get with the Columnstore index. Well, it is a secondary index or non-clustered index. So we do still have to store the heap or the B-tree. The heap or the B-tree can be compressed using page compression to save space, but this Columnstore index, for now, in Denali, is an extra structure. We're going to work on making it a clustered index, so at some point in the future, we'll introduce this as the primary storage structure for data. You can anticipate that, but in Denali, it's a secondary index. Yes.
Because you also mentioned that you were compressing the data.
So
you used less disk space, but you're storing it twice now.
We are storing it twice. However, it's not as bad as it sounds. Here's why. Virtually all queries will be processed against the Columnstore. So the the B tree or the heap will just sit there on disk and not be brought into memory. So in terms of query acceleration, this gives you it's as good as if it was the only copy of the data. So it does take extra space. Question in the back. What's the effect on writes? So the data is read-only once you create a column store index in Denali. You can, however, switch in a new partition to add data. I'll talk about that later as part of the talk. So this column store index can be partitioned. Of course, it must be partition aligned. You can't have a column store index that is non-partitioned on a partition table. The index must be partition aligned. You can't have a column store index as an index on top of an indexed view, and it can't be a filtered index. So there are some limitations, but we think that these aren't showstoppers. We've talked to a lot of customers about the scenarios they have with data warehousing and feel that what we've introduced in Denali has a ton of value, and people can use it and accommodate these limitations. So when you create a column store index, you create a table, you load data into that table, and then you run this index create statement, and there's an example. So an interesting thing about the column store index is that it has no key. A B tree, the only indexes you're familiar with are indexes that have a key, like a B tree. All right? The column store index, when you create it, you list out the names of all the columns you want to include in that index. And those columns are represented as one of the stored columns in the column store. Any columns you don't list are not included in the column store. Well, typically, so the question is, the column store is not a true duplicate of the data, right? Well, typically, you will include every single column of the table in the column store. And I'll talk about there's some data type limitations. Some data types cannot be included in the column store, and I'll get to that. So yeah, usually you include all the columns. You may omit some of them.
Do you have to specify them all, or can you use like asterisks to say all columns?
You have to specify them all. Yeah, the question is, can you use a star to specify all columns? The answer is no. You gotta list them all out. And there is a dialog box that makes it easy to create the column store index now in Management Studio. So the dialog box on the upper left is an example of the column store index creation dialog, and you can just click the top upper leftmost checkbox and it'll select all the columns, and you just say OK, and it will just create a column store on all the columns. Or if you want, you can omit some of the columns. You can check that upper left box and then uncheck some of the columns that you don't want, for example. All right, that's an excellent question. The question is, now that you have a column store index as an option, will you want to use other non-clustered indexes on the data, say covering indexes, to accelerate some other queries? The answer is probably not. Okay, so in the past, if you had a very wide fact table, say with 100 columns, you might have a lot of queries that only touch, say, 10 or 15 of those columns. So you might create a covering index that includes those 15 columns to accelerate those queries so that you don't have to scan as much data. That was kind of a common practice in the past. Sure. Typically, you won't need to do that anymore.
Well, take that one step further. Does the non-clustered index become irrelevant?
Does it become irrelevant at this point? For most decision support applications, yes. If you want to support seeks, So B trees are still going to be more efficient than a column store at supporting seeks. Okay? So most decision support applications don't need to do seeks anyway, so if you don't need them, then you probably just need a cluster B tree with a column store on top of it and no other non-clustered indexes.
So range stands for specific columns, column store index.
Yes. Okay. Yes. Question? So if okay, I think you're asking if you want to truncate the table, can you do that with the index still there? That's a good question. I haven't actually tried that. I think it will work, but I haven't tried it. Good question. We can if you want to come up after, we can experiment. So query optimization with the column store has been tuned for the column store. We still use a cost-based query optimizer. So the optimizer will choose the column store or a B tree or a heap, depending on what it thinks is the most efficient access method for the query. Like if you do a query like select top 1 star from T that has a column store index, it'll probably use the B tree or the heap to run that query because the cost of reassembling all the columns into one row is probably greater than just reading the first page of the table and displaying the row. So, or doing a seek is going to be more efficient using a B tree than using the column store. If you want to do like select the maximum value from a certain column that has a B tree on it, it can just seek to the end of the B tree to find that. So the optimizer is going to choose which index to use to solve the query. And the optimizer also will try to choose these new batch mode query execution operators. I talked about the batch mode of query execution. The query optimizer will select those operators when appropriate to accelerate the query. If you want to tune the way the query optimizer chooses a query plan with a column store, you can use hints. You can use the existing index hints that many of you are familiar with. For example, if you want to use a column store index and the optimizer is not choosing it, if for some reason it chose the B tree instead or the heap instead, you can just say with index and then the name of the column store index to force it to use the column store index. Or if it's for some reason the column store index is causing a query plan to be chosen which is less efficient than the B tree, you can force the use of the B tree, again using an index hint. And finally, we've run with the column store index on complete decision support workloads. And the query optimizer works with the best information it has available, but sometimes there are cardinality estimation errors or other problems that might cause choice of a bad plan. And we have seen in some cases that when you add a column store, you might have a workload with 100 queries in it. You might add a column store and maybe 50% of the queries run insanely faster. Maybe 45% of them don't get much better. They're about the same. And a few percent, maybe 5% out of those 100 might actually run slower with the column store because of bad plan selection. So in that case, we've added a new query hint that basically says ignore the column store indexes. And that gives you at least the same performance you were getting in the past with the B trees and heaps. So if you're willing to go in and tune those queries, it's usually not too hard to rewrite the queries or use other hints to get them to perform better. But if you just want to apply a column store index in an existing system with a lot of queries and you get a few regressions, you can use this ignore non-clustered column store index hint to get at least back to where you were for those queries that may have regressed. So over time, the optimizer will improve, but we have seen some regressions when you just add a column store index to an existing workload. Question? I'll show you that later. So the question is about show plan. What does it look like? And I'll show you some examples of that. I talked a little bit about memory management with the column store earlier. And again, the column segments are the unit of replacement in this new object cache we use for data from the column stores. So this illustration shows that maybe we brought one chunk of data from column C2 and another from C4, and they're stored in this object cache in memory on the right. And again, we don't double buffer, so we do have to read 8K pages from the disk when we bring in pieces of those large objects that represent column chunks or column segments. But those are freed immediately once we create the column segment object in the special new in-memory cache.
Is there a fixed amount of space allocated to that cache? And is that in the buffer cache or is that somewhere else?
The question is there a fixed amount of memory allocated to this new special type buffer cache for column segments? And the answer is no. So there's now two caches. There's the page cache and there's this column cache. And there's a memory broker that we've implemented that can make either one grow or shrink depending on the needs of the system. Okay? So there are new show plan elements that indicate that you're using Columnstore or using batch processing in query execution. So on the top right, there's a new icon, which is a Columnstore index scan. So this is got a new icon that sort of indicates columns, and each column is a different length, indicating that columns can be compressed, so not all columns are the same size. And on the left, the upper left, there's a new type of operator called a batch hash table build. So for this new batch processing mode, there's a new kind of hash table that's used for hash joins. It's called a batch hash table. And so those are the two main icons that you'll see that look different from regular query execution plans. But otherwise, the plans look very similar. Now, I know the font's a little small, so it may be a little hard to see, but if you look at this yellow box in the middle, look towards the top, down to 3 rows and 4 rows, it says actual execution mode and estimated execution mode is batch. So each operator now has an execution mode associated with it. It's either a row mode or batch mode. So batch mode execution is typically much more efficient. So as you're tuning or debugging your system, if the query isn't performing as well as you had expected, check that execution mode and see if it's batch mode or row mode. If it's row mode, then you may need to tune or tweak the query to try to get it to be batch mode.
Can you force that?
The question is, can you force this? There's no way to force that right now. I'll talk about some of the limitations. This is version 1 of this new feature, and there are some limitations, unfortunately, where you don't get batch mode to kick in quite as often as you would like. And I'll talk about some ways to work around that using some query rewrites. Unfortunately, there's no really way to force it. There's no hints or anything to force it. We will actively, we're planning to enhance the system so that batch mode is used more frequently throughout the entire query execution plan over the next couple of years. But for now, we have basic batch mode processing, works mainly for the hash join pipeline that's typical of most data warehouse, the heavy lifting part of a typical data warehouse query. Now, in some rare cases, if there's not enough memory to perform a certain operation in batch, we might fall back to row mode. So in rare cases, you might see actual execution mode row and estimated be batch. So there is a fallback if there's not enough resources that might fall back to row mode, but it's quite rare to see that. There are some new index catalogs that are associated with the Columnstore index that indicate statistics about the Columnstore, data about the Columnstore segments, like how big each individual segment is. And also there's dictionaries associated with a Columnstore that are part of the compression system. So we use several types of encoding, but one of them is dictionary encoding. And so a dictionary is basically a set of values from a column. And what we can do is, for example, with a string column, you might have long character strings in a column, But if there's a small number of discrete values in that column, say you've got character strings like names that are 30 or 40 characters long, there might be 20 discrete values in a column, but millions and millions of rows in the table. We'll typically use a dictionary to store those unique values, and then just use a key like a 6-bit value as a lookup to look up into the dictionary. And we actually can compress down to the bit level. So a column that has only, say, 4 unique values in it might be represented by 2 bits per row, which are just used as a lookup key into a dictionary. So these catalogs can give you some insight into how the data is being stored. So Columnstore indexes are a native built-in storage structure in SQL Server. So as such, they just work with other parts of SQL Server, like backup and restore, for example. When you back up a database with a column store in it, the column store goes with it. It's a native part of the database itself. So most things like backup and restore, mirroring, log shipping, Management Studio, they just work with column stores. So we actually had some of the same people who worked on this worked on the first version of full-text search as well as the second version of full-text search. So I don't know if you remember, but full-text search, when it was initially implemented in SQL Server, actually used some files that were not part of the database. So backup and restore, et cetera, didn't work quite right with that. And then when we did the second version of full-text search, we brought all that stuff into the database. So we learned from that. The people really didn't like that experience, so we made it part of the database in version 1. The question is, are there any special considerations for fragmentation or reorgs, rebuilds? Honestly, I don't know. So far, we haven't discovered any, but people are just starting to use this feature. This feature is going to come out in CTP 3, which is due out in midsummer. And so we have some internal TAP customers that are working with this feature already, and we haven't heard anything about any storage management type issues that they're having, but that usually shows up over a period of time. So we'll have to gain experience with it probably by fall. After people have been using it in production for a while, we might know more, but I don't have any concrete answer yet for that question.
Well, is there any maintenance associated with it, or is it all implicit?
The question is there any maintenance associated with column store indexes, or is it all implicit? There's really no maintenance that I know of associated with it. You can't update a column store index. So once you build the index, it's in a fixed format. It's not going to get more fragmented.
What will happen if you do an update on a table with the column store index?
Right now, column store indexes do not support updates or bulk load. So I'll talk about how to accommodate that, how to update data using partitioning or some techniques where you can drop and rebuild the index. Okay? There are some data type restrictions associated with column store indexes, and the main one that you need to be aware of is that decimal data types greater than 18 digits cannot be part of a column store index. So we have seen some people using decimal with 19 or more digits. Usually people use that for no real reason. The data, we've seen, for example, someone was using decimal 22,4 as a data type, but they didn't have any numbers in that column that were greater than 18 digits. So you may have to modify your data before you build a column store index to make the decimal types be 18 digits instead of more than 18 digits. In the future, we will extend this to support decimal all the way up to the maximum size, but in the Denali release, it's going to be 18 digits will be the maximum supported. And also, unique identifiers are not supported. So unique identifiers are 16-byte quantities. And unfortunately, they're not supported in column store in the first version. So other things that are less significant, like blobs, cannot be part of a column store, but you don't put blobs in a data warehouse fact table anyway. That's just not a typical scenario, so that's not really that big a deal. Probably the biggest ones that may affect you are the decimal and unique identifier.
When you say CLR types aren't supported, does that include hierarchy ID and geography types?
So it does. So CLR types are not supported as part of a Columnstore. Again, these are, because this is a version 1 feature, we had to scope it. We had a team that could only do so much in the available time for this release, and we scoped it. So you can expect these things to evolve over time and be supported, but right now CLR is not supported. Okay, so there are some new date and time types that were introduced in SQL Server 2008 that like high resolution date time types that can take more than 8 bytes. So any date or time type that takes more than 8 bytes is not supported in a Columnstore index. So if you have a high resolution timestamp that takes more than 8 bytes, you'll have to change the resolution or use a different type. Yeah, well, so date time, I believe date time 2, I think you can vary the number of, you can vary the size of that, and I think it is supported if it will fit within 8 bytes, but if it won't, then it's not supported. Pardon me? Yeah, so the rule is that every single date and time type is supported as long as it fits in 8 bytes. If it has a number you can use to vary its precision, if the precision is small enough that it fits in 8 bytes, then you can use it. So there are some query performance restrictions associated with batch processing in the Denali release when you're using Columnstore indexes. And the main restrictions are that some operators like outer joins and unions, they work with Columnstore indexes, but batch processing does not kick in. And so that limits the performance gains that you get quite a bit. And you can consider modifying the queries in your application to hit sort of the sweet spot for Columnstore indexes and batch processing. And as long as you stick with inner joins that have grouping and aggregation, star join is not necessary, but often a star join that has only inner joins and uses grouping and aggregation, a piece of query like that will run extremely fast. You can have multiple subquery blocks in your query. As long as they all have that pattern, then those subquery blocks will run super fast with batch processing and using the Columnstore, and you can get excellent query performance if those are the query blocks that do the majority of the work in the query. So in order to illustrate this a little bit, in the interest of full disclosure, I'm going to demo for you an example of a query which isn't benefiting from batch processing, and then talk a little bit about how you can tweak the query to get that benefit back again. Let me assure you, we're working actively to improve this, and so that outer joins and unions and other operations will be supported with batch processing in the future. But let me demonstrate some of the limitations. All right, so this query here see that query 1, it says no batch processing. So it looks pretty innocuous. It looks like a star join type query because it's got the purchase table and the media table, but there's a left outer join there. It says left join. So unfortunately, that affects the ability to use batch processing. So I'm going to run that query. it'll take a while to run this query, and we'll look at the show plan. All right, so it took 15 seconds to run this query, even though it is using the column store. And let's take a look at the show plan. All right, so you see on the far right it has a column store index scan. Down here it's got a table scan of the media dimension, and then it's got a right outer join. So if we look at this, you see that it says row mode. The estimated execution mode is row, even though it's a column store scan, right? So that indicates that batch processing didn't kick in for this query, and that's why it took 14 seconds and not 1 second or less. So let's see what we can do about that. Does anybody have any questions about this so far? You see that it says row mode. I mean, the only reason this is taking as long as it is because batch processing didn't kick in. So the question is, do you get any performance benefit at all? And the answer is yes. If it's an I/O bound query, you will get quite a bit of performance improvement, because it's only going to read the columns from disk that are needed, and the columns are heavily compressed. But if it's a CPU-bound query, it'll be about the same as if you were using a row store, like a B tree or a heap. It's a good question. So if you look at query 2 here, this one is exactly the same as the other one, except it has just a regular join, an inner join. So just to execute it, do you see how quick it came back? It just took about a second, a little less than a second. So that's I want to be able to use my column store. What's going on? So what can I do? You can do some sort of query rewrite to get the performance back. This is not easy to do, but hey, this is something you can take away that will enable you to tune column store query processing in the event that you really have to use an outer join. So what I've done here, you see this query block here, the with clause has in it an inner join query that's the same structure as that second query Q2. And then after I've already grouped and aggregated the data so there's a small number of rows, then I do the outer join. And I join on the goal was, why did I structure this query with an outer join in the first place? What I really wanted was, so I have media, which is like movies, movie titles, and purchase, which is movie ticket sales. And I wanted to create a report that had one row for each movie title and the count of sales. So some of those counts are going to be 0, right? And that's a situation where you'd want to use an outer join. So because batch processing didn't kick in for that query, the performance wasn't quite what I wanted. So I'm using a trick here in this query rewrite where I've used an inner join to do the heavy lifting, and that's going to be processed with batch processing. And then it's going to be aggregated so that only a relatively small number of rows will be produced from that query block. And then I take that and do an outer join with the media table so that I can get those counts equal to 0. But because the media table is pretty small compared to the purchase table, that outer join will be quick, even though it happens in row mode. So let's look at the query plan for this. Actually, let's start with looking at the query plan of the second one. So this query plan here, you see it's got a column store index scan on the lower left, and this is an inner join instead of an outer join up here, this hash join operator. On the lower right. So if you look at that, it says estimated execution mode is batch. Before it said row. And so that, you want to see that batch. That's what's going to give you the really excellent query performance. Now, let's take a look at the show plan for this one. Query 3. Actually, let me run this one again and show you how quick it runs. So you see that ran. It gave us the query result we wanted had all the movie titles and 0 counts for those movies that had no sales. See the 0 counts at the bottom here? So this gave us the answer we want, and it ran super fast. It ran in about 2/3 of a second. And let's look at the execution plan for this one. So you see this piece over here? This is for the inner join block, that was in the with clause. And let's look at this and see its batch mode. Okay? So you can get creative and you can work around these problems, these limitations we have, and be assured that over time we're working actively to improve query execution so that inner joins and other types of operations are accelerated.
Optimizer could have done this.
Pardon me?
Optimizer could have figured this out.
Yeah, it's actually, the comment is the optimizer could have figured this out, right? And yes, the answer is yes. So we need we want to actually implement a batch mode outer join operator, and that hasn't been implemented. So we need query execution and query optimization work to make this work. So that was full disclosure. So it's a version 1 feature. The vast majority of the time, your queries just have inner joins anyway, so you'll be fine. But in some situations, especially for queries that are generated by tools that where you can't control the SQL, that'll probably be the area where the most difficulties arise. But if you can handwrite the queries, you can tune them to get the benefit from batch processing, even though it might require extra work. So we touched on loading and updates before. So you can't update data in a column store directly. So insert, update, delete, and merge DML and BCP operations, they'll error out. They won't succeed if there's a column store index already built on the target table. So, however, most data warehouse scenarios are sort of append only. You rarely update data in the fact tables. And so because of this, we can use partition switching to bring new data into the table that has a column store on it. And let me talk through some various update scenarios. The first method for updating a column store index is the simplest. Typically, you might have a nightly load scenario in your data warehouse or your data mart. What you can do during your nightly batch window is simply disable the column store index, do your updates, whether you're using BCP or update DML, and when you're done, rebuild the column store index. So it takes me about 6 minutes on a desktop PC to build a column store index on a 100 million row table. And so the index build is fully parallelizable. So for most people, unless you've got a really large volume of data, you'll be able to use this method. Okay? Is this an online operation? Can the data still be actively used while you're doing this? I think what will happen is that you won't be able to use so there's no online index rebuild for the column store index. You can't be using the old one while you're building a new one. I believe it would drop back and use the B tree or the heap underneath. So the query performance could be dramatically slower, but it should still let you run the query. The question is the index rebuild memory intensive? And the answer is yes, it is. Index rebuilds take more memory than a B tree build. So this is not a main memory database technology, but it loves main memory, right? Because index builds take quite a bit of main memory. The limiting factor is those million row segments that I talk about. That entire million row segment has to be in main memory during the index build. So as long as you have enough main memory to fit that, you'll be okay. It's formatting a separate blob for every column in the column segment. So let me recap this update method. Again, you disable the Columnstore index, do your updates, and rebuild the Columnstore index. So most people can accommodate this because we know that 75 or 80% of all data warehouses and data marts have a nightly load type scenario, and they have a batch window that's big enough to accommodate this. If your data gets really big, then you will want to consider using partitioning. And what you can do here, the reason you might want to consider using partitioning is because dropping the Columnstore index and then rebuilding it causes you to lose a lot of work that it took to build the Columnstore index. So if you want to avoid losing all the work and having to redo it, all that work that was associated with building the Columnstore index, you can use partitioning so that you can switch out the newest partition into a staging table, drop the index on that newest partition, do your loads into the newest partition, then rebuild the Columnstore index on that partition and switch it back in. So this works perfectly fine. And moreover, you can even do incremental loads during the day with this method. So for example, if you want to load every hour, if you have a very high volume of data coming in, you can create a new partition, split the partition. You'll have an empty partition at the end of your table. You'll split that in two and just switch that new partition with a Columnstore index on it into the table. And that will allow you to do incremental loads during the day, even though we can't insert data directly into the Columnstore. So there is a slight gotcha in prior versions of SQL Server. If you use no-lock queries, if you have a heavy query workload using no-lock queries, then that could starve the ability to switch in a new partition because the no-lock queries preempt the lock request for doing the partition switch. We are doing basically a bug fix in Denali to fix that. Now, however, if you're not using no-lock, you don't have to worry about this. If you're just using read committed, you'll be fine. Or if you're using snapshot isolation, you'll be fine. Now, suppose you really want to get fancy and you don't want to switch in a brand new partition every hour, but you want to, suppose you wanted to update every 1 minute or every 5 minutes. There is a way to accommodate that. It's pretty tricky, but you can do something like this. You have a partition table with a Columnstore index on it, and you keep a copy of the data from the latest partition in a separate staging table. It's a row-structured table. It doesn't have a Columnstore index on it. And as rows trickle in, you append them to this staging table. And you do the following indefinitely. You append that data to the staging table, say for some period of time, say 15 minutes. Then you put a Columnstore index on that staging table, and then using partition switching operations, you exchange it with the newest partition that's currently in the table. You'll have to use a temporary parking place to do that switch because you can only switch into an empty partition. But you can swap them, and then now you've got another table that's kind of behind schedule here in the staging table. You drop the Columnstore index from that, and then you catch it up. You insert the rows that have already been inserted into the primary table's newest partition, and then you start appending the newly arrived rows into the staging table again, and then you just repeat this process. So you can script this. This is pretty tricky, but it is a way to accommodate a trickle load type scenario with the existing feature using partitioning. So the question is, how is this different from the other scenarios? And you observed correctly that, yeah, the difference here is the frequency of data loading. But the basic idea is still you have to insert into a row store table, build the index, and and then you can query the data. Okay, that's a good question. So the question is, how do we see this interacting with use of OLAP cubes and MDX queries? So it's true that in the past, probably the majority of people that were using OLAP systems were using them just to get the queries to run faster. It's not because they loved MDX. Okay, that they probably would have been able to express their queries in SQL using regular reporting tools. So for those people that are satisfied with SQL, they like that as their way to express their queries, and they're using reporting systems that can let them display the graphs or charts or whatever they need as a result of those queries, they may now be able to just use the relational database and get that interactive query response time that they might have been getting before with the OLAP system, but use SQL. But there's other reasons to use an OLAP system, like the hierarchical data modeling, the advanced reporting capabilities you get with them. Now, with things like Power Pivot and Crescent, the developer experience developing reports with that is really slick. So we think that for some people, yeah, they may want to stick with the relational database because the queries are running so much faster now, and they may not need that extra moving part in their environment, the OLAP system. But others that want that improved semantic capability and they want to use the cutting edge reporting tools, they may continue to use OLAP systems. So time will tell how things will change. We're looking at so anyway, that's probably the best answer I can give now. Thanks. So you should build a column store index, again, if you have a read-mostly workload in a decision support environment. It's really not appropriate for a OLTP environment. Now, we probably will see people use this in OLTP-type applications, maybe in something like an operational data store that's part of the OLTP environment, but that's read-only, right? You can't update it, so it wouldn't be part of the data that you'd be updating. You want to put column store indexes on the fact tables in a data warehouse. Typically, again, you need to use column store indexes on the dimension tables, except in rare cases. If you have a monster dimension table, like I know some big banks, like Bank of America, probably has a 300 million row customer dimension. All right. If you want to be able to query that super fast, it might make sense to put a column store on it. But typically, dimensions are much smaller. They're rarely more than a few million rows, and it's so quick to scan those with the row store that it's really not necessary to add a column store to them. So you don't have to go add a column store to every single table. Just focus on the fact tables and maybe your monster dimensions. So you don't build a column store index if you have to update data frequently, or if you can't accommodate the restrictions that I talked about associated with data loading, then don't use a column store. In rare cases, like in Denali version 1, if we don't support batch processing for outer joins and every single query in your workload is automatically generated by a reporting tool and has outer joins, then you might not want to use column stores in that type of scenario. So today I've told you about a dramatic new query performance acceleration feature in the SQL Server Denali release. It's a column store index combined with a new query execution and query optimization method called batch processing. And together, these two things give amazing query acceleration and really astonishing speed-ups for data warehouse type queries. And we think that you and your business analysts and end users that are using your systems are really going to love this new query acceleration technology. So thank you for coming. Please be sure to fill out your evaluation. Thank you very much.